Well, at the end of the last lecture, I was making rather a bad job of explaining the way the quantum field theory point of view on the wall correction to the additivity of the signature. So I'll take a step backwards and try and get to that once again. So I think I'll start off with the concept of what I call a three-tier. I'll give a formal definition. A three-tier d-dimensional quantum field theory. So this is going to have 3 layers of structure instead of 2 layers of structure. So again, we consider manifolds which are closed and oriented, or else cobordisms between them. So the manifold will always be compact with or without boundary. And we start off in dimension d minus 2, a closed. And we associate with this some kind of complex linear category. Which are called C sigma. So an example of the kind of thing I mean is the category of A modules, A sigma modules, for some algebra AC over the complex numbers. Now, of course, what kind of algebra, what kind of modules and so on will depend on the situation. Now, through the cobordism, the d minus 1 dimensional cobordism, like that, we'll associate to that an additive functor. I'm going to, for rather strange reasons, perhaps write H10. So we'll have some examples, of course, presently. And then finally, to an M, which is going to be a d-dimensional manifold, so this is going to be an actual space-time. This is going to be a cobordism between, in a situation like this, we have 2 d minus 1 dimensional manifolds, and we have a cobordism n, and another cobordism here, n prime. Then I'll think of this as being some kind of transformation like that. So we think of a picture like this, where we have 2 manifolds, 2 cobordisms. These 2 things together form a closed manifold with boundary and corners, and M is something that fits in between the 2, like that. So that's the picture you have in your mind. So in that situation, we get the transformation of functors. Which I write um from hn to hn prime.
What do we expect if n is closed, so sigma is n?
Yes, I'm about to say that. So, in particular, we're going to put the same 3 axioms. So, the axioms are some kind of smoothness, which I won't mention anymore. And secondly, concatenation. Now, there are now 2 kinds of concatenation, in that we can compose the cobordisms n, or we could concatenate these cross cobordisms like that. And in each case, the things compose. And thirdly, tensor. Now, tensoring means the same as in all the other cases, except that, you see, in order to make sense of it, we've got to know that if we have two disjoint d minus 2 manifolds like this, then we want to say that the category associated to this is meant to be, in some sense, the tensor product of two additive categories, two linear categories. So we have to decide what we mean by that. Well, we want certainly some kind of transformation like that, which will be an equivalence of categories. But of course, in order to decide what you mean by this, you'd have to be more precise about what class of linear categories. And I'm going to say some more about that. But you see, if this category was A sigma naught modules, where this was some algebra, and this category was A sigma 1 modules, then what I have in mind by the tensor product of these two categories would simply be the category of modules for the tensor product ring. And that's what I have in mind, but of course, in order for that to make sense, even then one has to decide exactly what one means by the tensor product. Well, one of the, so just as in the case of the two-tier structure, there are lots of simple things you immediately read off. For example, if sigma is empty, that implies by exactly the same rule that C sigma is just the category of vector spaces, finite dimensional vector spaces. In fact, finite dimensional. Because you see, it has to be a category which for any other category C has the property that this is somehow equivalent to C. But you see, if you have any complex linear category, you can always tensor its objects with finite dimensional vector spaces. So you always have this relation, and that is the only category with that property. You see, so in particular, you see, suppose we had a closed end, then a closed end we could think of as a coordinate like that. So it would be a transformation of functors which was additive from vector spaces to vector spaces. And of course, because it's additive, it will be completely determined by what it does on the complex numbers of any finite dimensional vector spaces, the sum of copies of the complex numbers. And this will just then be a certain vector space, Hn, and so we'll get back our previous data. Actually, even this, you see, I was sort of assuming in that discussion that I was talking about topological field theory, because when I said this had to be a finite dimensional vector space, if I put some more kind of topological ring, I could have made this true with some class of more general vector spaces. I just want to say the whole thing schematically first of all. So you see, this would, if we restrict to cases where sigma is empty, we just have the structure we had before, but now we have some information about how to cut our codimension 1 things along codimension 2 things. So the example that I want to consider an additive analog of this structure. In the following sense. You see, there we were associating codimension 2 things to linear categories. Well, a linear category is a kind of category. We could relax that and consider some more general kind of category. On the other hand, among categories we have groupoids. So supposing I want to talk about invariants that I write additively, and the example of the signature will be one of these, then I can use the following thing. So sigma d minus 2, we're going to associate with a groupoid. So a groupoid is defined effectively. And the groupoids that I'm going to consider are going to be a very restricted kind. They're going to be the fundamental groupoids always in space, and it will be some space naturally associated with the sigma, for some sigma. And in all the examples, the spaces are going to be connected spaces with fundamental group equal to the integers. So that's the only example that we're actually going to meet. So this is not going to be a very general kind of groupoid particularly. And, well, again, a D minus one-dimensional coordinate will give us a transformation of groupoids. And I don't even bother to write it down, exactly the same formal structure. Now, in order to make this clear to you, I'll take a very, very simple example. So let's talk about the Gauss-Bonnet theorem for a surface. And then I'll come back to the signature. Now remember, you see the Gauss-Bonnet theorem is about the following situation. Suppose you have a surface which has a Riemannian metric, then it has its Gauss curvature 2 form, and the Gauss-Bonnet theorem for a closed surface says that the integral of that curvature is the Euler number of the surface. Now I'm interested in making the invariant picture theory, so let's think of the two-dimensional theory defined on Riemannian manifolds, so we only have a curvature form when we have the Riemannian structure. I'm interested in discussing the sense in which this is local. You see, I explained last time that on a certain way we can think of the Euler number as a topological invariant, and when you do a cobordism of surfaces, the Euler number adds, because one-dimensional closed manifolds have Euler number 0. On the other hand, you can't just say the Euler number of the simplex is 1, but you can't get the Euler number just by adding together the number of simplexes in a simplicial decomposition. So let's discuss what structure we have here. And this example is meant to be good for illustrating another point. Just as in my initial discussion, I explained that the codimension 1 manifolds, the ends, were really germs of d-dimensional manifolds. So they were really little neighborhoods. And similarly, it should be the case that when I consider the d minus 2-dimensional manifold, what I really mean is again a germ of a d-dimensional manifold, so 2 dimensions up, sitting around it.
All these manifolds are C-infinity.
Yeah.
Yeah. Good.
So let's give you an example of this structure. You see, supposing we take D, so I want to just go to a 2-dimensional example, so D equals 2, so we have to say what a point does. Now, a point, we want to associate to this, first of all, P of a point, which is going to be the directions at P. You see, remember, our point is not-dimensional, it's a codimension 2 thing, but it sits inside a germ of a smooth surface. So we have a circle of directions that we can go along the surface from that. So this is, of course, a circle. And if it's an oriented manifold, we should think of it as an oriented circle. That's actually important, but I won't want to go into of P of a point. So it's a category whose objects are directions, and the morphisms from any direction to any other direction. And when you have 2 such directions, the morphisms are the homotopy classes of paths in this circle, beginning there and ending there. So that is a Z torsa, so hom in the category, from a direction L to a direction L prime is a Z torso. In other words, it's something on which the integers act, it's a set on which the integers act, and it's exactly a copy of the integers, but it doesn't have a particular base point.
So
Well,
point
it
is a
looks like
germ?
the preferred base point. Okay?
Point is a germ, or P point is the germ of the manifold?
Yes, so a point is a germ. In general, all of these lower dimensional manifolds are meant to be germs of d-dimensional manifolds.
Yeah. So how do you define the fundamental group point of a germ of a manifold? Because I mean, it depends.
Well, the
large-
directions just only depend on the tangent space.
Okay, so of course.
So it's just a direction.
Okay, so
it's just a ray
It's just
in the tangent space.
yes.
Okay, so now I want to say what happens when we have a map from P0 to P1, and N. This will be a path, a one-dimensional manifold, and remember it's always a germ like this. But you see, we're now on a Riemannian surface. This is meant to be a germ of a Riemannian surface. So we have the circle of directions there, and the circle of directions here. So parallel transport on the surface defines a map from the directions at the beginning of the path to a direction at the end of the path, and hence defines the map. So I'll just write parallel HN is defined by parallel transport. Along path N. So, in particular, what will happen if we take a closed path? So we can think of what happens. We can firstly have a closed path, like this. Then that we should, what will we get then? Well, we should get a Z torso, right? One thing I didn't explain is that in this theory, just as the thing associated to the empty D-2 manifold is the space of vector spaces, this will be the category of Z torso itself. The category of Z torso. An object just is a sector of Z action, and we consider equivariant maps from one to the other. So how do we associate such a thing to a closed surface N? Well, we can cut it like, say, in 2 points like this, and think of it as a composite of something going from the empty set to these 2 points, and the torso will be the fundamental group of the tensor of those 2 torsos, and it will go to here. So what you will, I claim, what this will be is you can identify so for a closed path, N, the in Hn is the Z torso alpha n plus Z contained in the real numbers. So this is all real numbers congruent to some particular real number. Well, what will be the real number? Well, you see, if we do parallel transport right down that path, then we will come back rotated through an angle which is the horizontal, which is well defined, perhaps I should write over 2 pi of parallel transport. You see, when you move around the closed path with circular directions, rotates by a certain amount, this gives you an angle of rotation, and we consider all things congruent to that log z. The angle of rotation is really only defined modulo 2 pi, divided by 2 pi, it's defined modulo z. Now, so why is this a good thing? You see, remember what we're really trying to do. So this, well, and finally, of course, what will be um for a surface with boundary, a piece of surface with boundary m? Well, it doesn't have to be topologically a disk, but imagine this is n and that is m. Then we'll just define this to be the integral over m, that's again 1 over 2 pi, of the Gauss curvature, where this is the Gauss curvature 2 form. Right, now, you see, this is in Hn, because you know that the Gauss-Bonnet theorem precisely tells you that the integral of the Gauss curvature over a surface with boundary is the geodesic curvature of the boundary. So it will be something that lies inside this torso and so on. So you see now, the thing that was that I've done by this method, so I've been a little bit sketchy, but essentially what I've done is, supposing I have a surface divided up into little pieces, triangles or other curvilinear pieces. You see, if I wanted to associate to each little piece of surface an invariant which just lay in some sort of vector space or something which was associated to the boundary of this little piece, then in the theories that I was talking about before, I would have to associate an integer to each one of these bits. And as we said, you can't get the global Euler characteristic by just adding together an integer contribution. On the other hand, we certainly know that we can get the Euler number by adding together the integrals of the Gaussian curvature over all these things. And the important thing is that the integral of each over each curvilinear cell of the decomposition lies in something which is this Z torso. You see, so I haven't quite explained the full structure of how in general I will put together all the torsos. I will come to that presently, but at least in this elementary case you're meant to be able to see it straight off. That they're the things that you should add together. Well, so now let's go back to the example of the signature, which we had last time.
At the first one will suspect that the transport depends upon the connection.
Okay.
That the transport will connect in general certainly will depend upon the connection.
Well, it depends on the Riemannian structure, right? We have a Riemannian surface, so I'm talking always about the Levi-Civita connection.
Okay.
So just normal parallel transport on surface. So let's now come back to the the case of the signature. So now we're at t equals 4 in the case of the signature. So this is another one of these additive theories. So we're going to have a groupoid. So sigma will be a two-dimensional surface. It's going to take P sigma, I explained this last time, is the space of Lagrangian subspaces in H1 of sigma with real coefficients. So we have the middle homology of the surface. That's a real vector space with a skew form given by the product. And I consider the space of Lagrangian subspaces. That's a space whose fundamental group is the integers. And so C sigma is the fundamental groupoid of that. Well, I should have maybe, well, I'll leave you to see why it is that C sigma 1, sigma naught, just cross C sigma 1 minus C. That comes from a map P sigma naught cross P sigma 1. So I want to sort of spell out all the algebraic structure. It's not very interesting. But the important thing is that a three-manifold N with boundary sigma defines an object of C sigma, that is to say, a point of P sigma. And further, but I won't bother to explain this now, if we had a cobordism, if n were actually a cobordism from the sigma naught to sigma 1, it would actually define a map from P sigma naught to P sigma 1. But I don't really need that, so I think I will spell it out. So I want to explain that we said that when we cut a closed four-manifold into two pieces by a three-manifold, there's the Novikov additivity, which tells you the signature simply adds. You can assign a signature to a manifold with boundary. It's the signature of an indefinite quadratic form, and the things add. But the point is that that isn't the optimal way to look at the situation. It's really better to associate, so we want to associate a Z torsa to a closed three-manifold. So that the signature of a manifold N is in this torso associated to its boundary. Just as it was better to think of the Euler number of the curvilinear simplex as not being just an integer, but to be actually something in a set of real numbers which was a translate of the integers inside the real numbers. So we want to associate such a thing here in the same sort of way. Now, the way that fits in with So, well, from one point of view, let me say right at the beginning, just as with the Gauss-Bonnet theorem, this was done long ago by Thiers, Picodi and Singer. The thing that we want to do is that this will be the eta invariant. This invariant will be the eta invariant of m plus z inside the real numbers. The eta invariant is some number, which for the moment doesn't concern us, but it's a real number which we associate to a closed three-manifold. It's made out of the spectral decomposition of some, essentially, the Durand operator on the differential forms on the boundary. That's the boundary. And the analog of the Gauss-Bonnet theorem is that if you consider the Hirzebruch signature form, which is the signature analog, so to speak, of the Gauss curvature, if you integrate that over the manifold of the boundary, you get something which is congruent to this eta invariant modulo of the integers. So, one way of getting this is by index theory using the eta invariant. But I want to go a different route. I'll mention a number of ways in which we get this thing. But the way that's sort of relevant to the discussion is and supposing we have n3, and suppose that n1 union n2 join together along sigma. Remember, I gave the example of a complex projective plane cut into three pieces according to the size of the three homogeneous coordinates. So we divide CP3 into three four-discs. Whose triple intersection is a torus, S1 plus S1, where the three homogeneous coordinates all have absolute value 1, say. And each of these things is a true sphere. Well, so this is meant to be closed. And I want to tell you what this thing is. Well, remember, I told you what P sigma was. That was the space of Lagrangian subspaces. And when we have an n1, and here is our sigma, so this is meant to be sigma, and this is meant to define the boundary value of the one-dimensional homology of this is a Lagrangian subspace in the middle dimension there. So this defines a point in there, and this defines a point in there. So we want to say the Z torso Hn, this is Z torso of paths from, I guess like n0 to n1 and n1 to n2. In the fundamental groupoid of P sigma. Right, so you see here we have something which is actually a three-sphere, which is made up of these two things. Let's call them n1, n0, and n2, say. So here we have, inside our one space P sigma, we have 2 points, one corresponding to this and one corresponding to that. And so we will think of a picture like this. We'll think of starting with the empty d minus 2 cobordism, and then do a cobordism n0 to sigma, and then we will do a cobordism n1 to the empty manifold. The composite of these two cobordisms is this closed three-manifold, which in fact in that example would be a sphere. The associated to this, we have the fundamental groupoid of sigma. And when we compose these two things, we're simply looking at paths from one to the other. So this is a Z torsa, which will be the composite going from there to there. Now we have, however, another cobordism, N1 and N2 from there to there. And when we do the composite of those, we'll get another closed three-manifold, a cobordism from nothing to nothing, which will be this one. On the other hand, in the category of, you see here we have two different cobordisms. So let's write it like this. We have two different cobordisms from nothing to sigma. We have this thing, let's call that M02, which is a cobordism from that to that. You see, that's a four-manifold which moves between those two cobordisms. So, you see, this composite going from there to there was something which we called H of N0 union N1. On the other hand, this one is the Z torso which we called H from N2 union N1. On the other hand, in this category, you see, we're meant to have a transformation of functors corresponding to that cobordism. So we ought to be able to associate to this something from this Z torso to this Z torso. Well, we can obviously do that because in our space C sigma we have the three, we're on the one hand looking at the Z torso paths from there to there, one looking there to there. On the other hand, this thing clearly gives us a path from there to there. You see, so our total picture is like this. We have empty sigma, empty, and then we have the empty cobordism from here to here, and the empty cobordism from here to here. Well, you see, this bit of the manifold, which we might call M01, gives us a transformation of functors there. And between that and that, we have one which we should call M12. And from this across there, we have M02. And we finally, you see, get something going from the empty four-manifold to the empty four-manifold, so an integer. So we've made the integer invariant with a composite of three terms, and when you track that through, it's simply looking at the homotopy class of that loop made out of, which I tried to explain in the last step. Well, I'm a bit behind schedule, so I was going to explain a number of different reasons why we ought to expect to associate a Z torsa to a closed odd-dimensional manifold. In this case, a three-dimensional manifold. So one way is by this eta invariant process, but there are at least two other ways. One is to think about cobordism theory. Cobordism theory constructs spaces with manifolds of any dimension in such a way that a closed d-dimensional manifold can be regarded as a loop in the space of closed d-1 dimensional manifolds. So you can look at these successive spaces of manifolds and use the sort of index map, the signature map, to map one into a purely algebraic situation. One can do that by index theory, and that's essentially what the eta invariant does. And one will associate the odd-dimensional manifold the space with the homotopy out of the circle. Alternatively, you can work completely geometrically. You can replace manifolds by their chain complexes with quadratic forms, and there's a cobordism theory of those things, and that will also give you such a map. But being so far behind schedule, I think I'm not going to say any more about that. Because I want to I want to get back more towards analysis and more towards general physically interesting theories rather than things which are purely topological. But before quite doing that, let me spell out what happens in the case of a surface divided into curvilinear polygons. So we'll now go back to the case p equals 2. And we have this invariant um defined for a closed surface, probably with Riemannian structure and so on. Now you see, supposing n is divided up into curvilinear pieces. They don't have to be triangles, they can be anything you like. So pieces like that. Now we can cut it up very small, and we'd like in general to get this number, this is a number, as a sum of contributions from small pieces. But actually I'm going to subdivide it even further, because given any vertex, I'm going to actually look at some terminals around the vertex. Take a typical vertex and look a little way, imagine it's like an electric circuit diagram, and imagine you put some terminals there. But let's not even just put one terminal, but let's put sort of an incoming and an outgoing terminal on each edge. So we put 2 terminals on each piece like this. So if we have 4 edges coming in there, we'll have 8 terminals. And so the terminals are indexed by a flag in the decomposition. You see, this terminal is indexed by giving that vertex, this edge, and this face. So whenever you have an edge, a vertex sitting inside an edge, sitting inside a face, you get exactly 1 terminal. And they come in 2 kinds, positive terminals and negative terminals. The positive terminals are the one where that is going anti-clockwise. The negative ones, so that's the positive one, that's the negative one, positive, negative. The negative ones are where the flag goes negatively in orientation. Well, so maybe I have colored cloth. So what I'm going to do is, so I have terminals. I'm going to make kind of decompositions like this. And I need one, the other time will have to be white. And then one third colour. So the white ones can be these. Then we'll have some red ones coming to a white, and then there'll be some blue ones, more white ones. And red ones like this. Now, what I want to do is make this invariant come from a contribution from each of the cells I have here now. So I have one cell around each vertex, which is obviously a little disk around each vertex. I have a little strip around each edge, that's meant to be a small rectangle. And then I have the faces themselves, which are meant to be small cells. So I want to think of the terminals. Let T plus and T minus be total set of terminals classified as positive terminals and negative terminals. Let's take the disjoint union of those. Then, starting with the empty set, the empty North manifold, I have two cobordisms ending with these terminals. One will be the one that goes, I'll just write white. And the other, which will be the red one. Like the ones that go over the edges. Each of those maps the set of positive terminals to the set of negative terminals. So you think of each one of those edges as being something that takes one negative to one positive. So this is a lot of intervals regarded as cobordisms from the empty North manifold to this North manifold. We have two such cobordisms, and we have a cobordism between them. These red areas are a cobordism between those two things. Now, supposing we look at the cobordism, must be too brilliant. Now let's consider the blue cobordism. That's the things that go around each of the vertices. If I compose these two, I compose the white ones and the blue ones, then the composite from here to here is clearly the union of the boundaries of the vertices. I'll just write boundaries of vertices. So the union of those two cobordisms is a lot of disjoint little circles, one circle around each vertex. On the other hand, if I look at the composite of those two, that will also be a lot of little circles, one circle around each vertex. So these two composite cobordisms are each disjoint bunches of circles, small circles, one for each vertex in the one case, one for each edge in the other. So now let's make a cobordism from the empty cobordism, from empty to empty, where here we put in the neighborhoods of the vertices. And that's a cobordism which fills in each of these things. And then conversely we can get to the interiors of the cells, interiors of polygons. That's cobordism from these things to nothing. So the complete cobordism, which is M, you see, is made just as I said up there, composite of three things. One which is a cobordism around each of the cell, one which will be one of these things which goes from, I'll perhaps come back to that in a second, and then finally we compose one which fills in each of these little cells. So each of these things is completely decomposed into individual pieces which are totally disjoint from each other. So let me just say a little word about let's talk about one of the red cobordisms. We have two incoming vertices and two outgoing vertices. So I'm just going to magnify one of those rectangles. And we have a cobordism like that. And we have a white cobordism which went and the edges gave us the cobordism that fitted in there. That was a cobordism between the cobordism. We have two different cobordisms from two negative points to two positive points, and we have a cobordism between them. Now, you see the two positive points, they will give us C equals a point, tensor C equals a point. And So the edges will give us a functor like this. So we have two functors corresponding to the white one and the red one. And this cobordism is a transformation between them. Now, the algebraic structure that we need, if these were the categories of modules for some algebra, this would be a tensor A module, and this would be a tensor A module, and the cobordism would be, in order for this cobordism to exist, you find that the algebra has to be Hopf algebra, it has to be a Frobenius algebra, and the transformation of modules is the one which you get by the algebra map from A tensor A, which only exists for Frobenius algebras. You can have an algebra map which will convert. Suppose we have a bimodule for this algebra, and suppose so it has an action of A tensor A on that side, and an action of A tensor A on that side. Supposing we want to change this bimodule so that A tensor A acts by the flipped thing on this side, then you can realize that in the Frobenius algebra by a certain map on the module, which I won't bother to write down, and that kind of characterizes the algebraic structure. But in fact, this little transformation is something which is purely associated to this small region. Anyway, so it's something we can write down as a small contribution. I was at first planning to spell all out that properly in the case of the two-dimensional Yang-Mills, where one could kind of prove in detail all of these things and write the invariant as a sum of contributions for small regions, but it is quite complicated, so I'm going to go on and say something else. But at least I hope I've sort of shown that this is a systematic way, if we're prepared to go down to code dimension 2, to write a two-dimensional quantum field theory invariant as a sum of contributions coming from individual small regions. Now, I think the only other thing I have time to say a little bit about in today's lecture is three-dimensional Chern-Simons theory. So that means that my final lecture is going to be much more analytical about von Neumann algebras and that sort of thing, because I want to talk about this structure in the two-dimensional case, but for theories which are not. Essentially, I've been talking about topological theories, even though, as you see with the Gauss-Bonnet case, you needed to promote it to something metric dependent in order to make the invariants come bit by bit. So I want to, the most complicated thing I'm going to be doing in my lecture will be the case of three-dimensional Chern-Simons, which is another three-tier theory, and which will be relevant in analytic theory. So I'll just say it very, very quickly now, and then we'll be all I have time for today. So the next topic is three-dimensional as a 3 and 4-tier theory. So the 4-tier will only be in Wednesday's lecture. So this is a topological field theory. So what's it going to do? It's associated to a group G, the compactly group G, and a class. an element which is traditionally called the level, which is an element of H4 of the classifying space with integer coefficients. So it's something which gives you an integer invariant for every G bundle on the 4 manifold, although that isn't especially relevant. Now, I very quickly said in an earlier lecture that this could be promoted. These characteristic classes for cohomology of compact groups could be promoted to things which I call Deligne-Cheeger-Simons cohomology. Remember, these were things which, if we're talking about 2 dimensions, you can think of the 2-dimensional integral class as the isomorphism class of a complex line bundle. This would be the isomorphism class of a line bundle with connection. So things like the first Kondragen class, which you might have in the classifying space of an appropriately group, like a special orthogonal group, that can be promoted to a characteristic class for bundles with connection, which live in this theory. Remember, these things were meant to be 3-dimensional field theories defined on manifolds associated with bundles with connection. So this class, this level, gives us something. The level associates, among other things, to a closed 3-manifold, goes to a line, a complex line. An element of a circle, and to a closed 2-manifold goes to a complex line. And anyway, so this theory is defined by saying that the action for the theory so we have a notional space of fields on a 3-manifold, which is meant to be isomorphism classes of principal G bundles on M with connection. So this class, the level, gives us something in the circle associated with a closed 3-manifold. See, it would give us an integer if we had a bundle on a 4-manifold, but on a 3-manifold, it gives us something in the circle. So the action is just precisely this level, which goes into the circle. And we want to do the path integral corresponding to that. And the So what is this theory? Well, I claim it's going to associate a closed 1-manifold S, the category CS, which is the category of representation essentially of a loop group, the maps of S is the 1-manifold into G, which are positive energy, in the sense I won't describe, of level, of given level. So the level defines for you a very nice class of representations of this thing, which is essentially a loop group. Now, when we have a coholism from a bunch of circles to a bunch of circles, this is going to give us a functor, call that S naught S1, sigma is the surface. It's going to give us a functor, HS. Now, the most important case of this is going to be when the surface is a pair of planets like this. And that's going to be a functor this is going to be the same as c of x, which is going to be in s, which is called fusion. So this is a so this just depends on the topological surface, which is a pair of planets. And this is an operation which makes these representations into a Brady tensor category. So I'll say a little bit more about that next time. And finally, in particular, you see, if we had a surface which was closed, or a closed sigma, that will go to the vector space, a finite dimensional vector space. H sigma, and a 3-manifold, which is a cobordism from one of these things, will give us a transformation in the usual way, un H sigma naught to H sigma 1. Now, I want to explain some of the, I'm already over time, so I'll stop now. I'm going to explain some of the implications of this because it's a good example of, although this is a topological field theory, these loop group representations are on infinite dimensional vector spaces, Hilbert spaces. And the problems that we face when we try to unfold this picture are precisely analytic style things. When we have a loop group and a representation of it, so we have a circle and a group value function defined on that, the group of those things is acting by one of these positive energy representations on some infinite dimensional Hilbert space. And what we're interested in is how we, if we were to cut the circle into two pieces, in what sense can we factorize this loop group representation into some kind of generalized tensor product in some complicated tensor product associated to the two parts into which I've cut the circle. Now, that's a very difficult problem, and there are various approaches to it, but they all involve real analysis. It's not just simply a matter of finite dimensional linear algebra, the way different with signatures and so on work. So I'm over time anyway, so I'll stop there today, and that's why I'm going to talk about one main thing. And a few more analytic questions, because I want to explain how to put a bit of analytic flesh on the field gear structure that I've described. These are group representation spaces, so we're going to be transferring representations of some infinite dimensional group, if you like,